And we start with data that I know that you're all aware of. This is, of course, a babbling brook, a stream cutting through the mountains. And it's surprising to notice, with all of the surface water that we have on the planet, what little of our freshwater resources are actually in the form of lakes and rivers. Always surprises me. Remember, I went to college on Lake Ontario, which is one of the Great Lakes. I mean, these things look the size of oceans when you stand on the shoreline. Yet all of the lakes of the world, all of the mighty rivers of the world, just a tiny percentage of our overall fresh water. Let's start first of all by noticing that by far the largest percentage of all of the water on Earth is not even drinkable. It is salt water. It is the oceans. I think you've been exposed to these percentages before. Oceans represent 97% of all of the water on Earth. And of course, that's undrinkable. Unless, of course, we go to desalination, which is also covered in this chapter. So the freshwater amount is a little bit less than 3 then, since the ocean is a little bit more than 97. And out of that fresh water, here's something that's truly amazing. Out of that fresh water, out of that 3%, here is the pie graph for just that 3%. 77% of that is unavailable to us because it's in the form of ice and glaciers. It's frozen, and so we can't use it for drinking water. Although we've tried. I remember reading an article 10 years ago or so about a Middle Eastern country that had more money than sense. And they actually sent tugboats up to the Arctic region, blasted away a piece of glacier, and tried to haul it all the way back to their country in the hopes of adding fresh water, because they are lacking fresh water in a big way. Didn't work out so well. So most of this water, fresh water, is unavailable to us. 22% of the fresh water that's available is below ground, and as I mentioned a few minutes ago, that's called groundwater, and that's commonly known as aquifer. And we'll talk more about aquifers coming right up. But here's the thing again that surprises me so much. Less than 1%, in fact less than 0.5% of all of the water on Earth, or of all the fresh water I should say, is surface water. Lakes, rivers, ponds. Truly amazing. And then remember that there is a tiny amount of water trapped in our atmosphere. Very important thing though, because that's the water from which we get our rain. So there's the breakdown. You should have some familiarity with it. Nobody's going to ask you the exact percentages, but you should in general understand that most of the water of the world is ocean. Only about 3% is fresh, and of that fresh water, 3/4 of it is trapped in ice and glaciers. And most of the rest of that is in aquifers. So we need to get our water from there. Of course, if you need to get water, you need to hope that you live near an aquifer. You need to hope that you live near an aquifer. In fact, most of the places on Earth do not live near an aquifer. Less than half, I believe it is, people in the world get their water from aquifers. We get ours from aquifers, but most people get it from lakes and streams, which means if they're going to drink that water, it's going to have to be treated before it ever gets sent to your home. Aquifer water does not need to be treated before it's sent to your home. We simply add chlorine in case there's any bacteria to protect you from getting a disease, and then it comes to your home. Here are the terms that you need for understanding groundwater, there's a nice diagram on page 237 to help you see all of these different terms. Take a look at them. If you know what they mean, then you're good to go. If you don't know what they mean, take a look at these terms. You need to know them. We'll go over a diagram in a minute on page 237. If you know what these terms mean, you're good to go. If you don't, you need to pay real close attention. As I mentioned, aquifers are groundwater, small spaces found in the permeable layers of rock where water is trapped. An unconfined aquifer is one that has porous rock as its walls, and that enables lots of water to slowly seep in or drip in. And this is called recharge. When an aquifer refills, it's called recharge. So the area on top of an aquifer, like our area here, is called the recharge zone. It's the place where surface water slowly seeps through the soil and recharges the aquifer. A confined aquifer is an aquifer that's made mostly of impermeable rock, and therefore the water flows into it very slowly. The problem with a confined aquifer is if we're pumping water out of that, it takes tens of thousands of years to recharge a confined aquifer. Water in the unconfined aquifer can be just days old, or weeks or months, and certainly years. So unconfined aquifers, easier to recharge. Confined aquifers, much harder. And of course, if we are taking water out of the confined aquifer, that means that it's not going to be able to recharge, and that's non-sustainable. The water table is the area at the top of the aquifer. And picture drilling down into the ground. As soon as you hit water, you've hit the water table. So the water table is the very top of the aquifer. And springs will come up from time to time. Springs are water that's fed from the aquifer under pressure, and that ends up feeding into a lake or a river. In our case, the St. Johns River is spring fed. And that ends up becoming surface water. These springs, because they are under pressure, are continually adding water. Here's that diagram I was talking about. Really nice pictures here. You can see the confined aquifer is the area inside an impermeable rock formation, and you can see that the recharge area for a confined aquifer is going to be quite small, because water will not just seep down into the confined aquifer through soil. So recharge areas of confined aquifers are quite small. On the other hand, the unconfined aquifer, and this picture is pretty accurate, unconfined aquifers are usually found more closer to the surface, and they usually have a top layer that is soil or dirt, and therefore they recharge much quicker. Rainwater will just seep into the unconfined aquifer, making its rechargeability much easier. You can see here, here's an artesian well. When you drill a well into a confined aquifer, because it's under pressure, you end up with an artesian well. Artesian wells are always flowing because they're under pressure. A well that's dropped into an unconfined aquifer is one that you have to use a pump of some sort to get the water to come up out of that well. Bring your questions. If you have any questions on aquifers and recharge zones, springs, etc., we will answer them. One of the problems we have then when it comes to aquifers around the world is how quickly can they recharge compared to how quickly we take the water out of them. Big problem. This is an aquifer in the middle of the United States. You can see the states here to let you know where this aquifer is. It is the largest aquifer in the United States. Here's all the states that all of the people in these states are sucking water out of this aquifer. It's called the Ogallala Aquifer. Sounds funny. Remember that name. It's been on both the AP and the ACE exam before. The Ogallala Aquifer, the largest in the United States. And you can see how much it has been drained over the years. In this diagram, we're looking at 1950 over here, and we're talking about 2005 over here. So you can see a big difference in the amount of water that's left. In 50 years, in 55 years, you can see the damage that's been done. It's been a great source of water for all of these years. Farming, we're talking about people that need water for drinking, we're talking about industry. All these different activities have contributed to taking the water out of the aquifer, until you see now that this aquifer is not recharging at nearly the rate that the water is being taken out. So this leads to wars between states, and indeed there's been lawsuits and counter lawsuits among all of these states trying to claim the water to be theirs and their right to pump that water out. What they're not realizing, of course, is they are all part of the problem, and if they don't all get together, they need to all become part of the solution of what to do about the water from the Ogallala. Someday, of course, this aquifer will not be available to all of these people, and especially the farming interests on which they rely.
A large underground aquifer can provide the water necessary for irrigated farming. An irrigation well is drilled below the water table into the aquifer. Water is pumped from the well and used for irrigating crops. If water is pumped from the aquifer faster than it is recharged, the water table will drop. Pumping may eventually deplete the aquifer of most of its water, so that it is no longer usable for irrigation. As the water in the aquifer is depleted, the aquifer may collapse somewhat, causing the land surface above to subside.
All right, a couple of important words there that you needed to notice. Remember when let's try to go there. When the well is initially dropped, there's plenty of water available, but see what happens when the water ends up going down below the water table. Now what happens? Well, now the farmer has to dig another well, and they're going to have to drop it deeper than the previous well. And when that happens over time, we have that problem called subsidence. Remember, subsidence was a term that we used in mining. Subsidence is the slow dropping down of land over time. And you can see what happens here. We'll talk about this again in a minute, something called the cone of depression. Here is that cone of depression, and this is one of those environmental terms that you need to be familiar with. What exactly happens here? Well, when the water table adjacent to the well is declining, then we get this area of a cone of depression, and that's the water table declining to the point where here's a dry well. You can see this well isn't even able to function anymore because it's above the water table now. This lowered water table happened because of heavy pumping. And as a result of that, you can see we actually have this area. It's called a cone of depression. Important concept for you in environmental science. They always like to ask you about cone of depression. And here's the other very important environmental issue that comes up that's mentioned in all of the textbooks, and indeed you'll see it on your exams. It's called saltwater intrusion. And this only happens to aquifers that are near the coastline, like ours. It's a big worry for us here in Florida. Most of Florida is served by an aquifer. The Floridan aquifer is the one that services us, and most of Georgia as well. And here's the problem. Once again, if we find that we are pumping water out of the aquifer at a rate higher than the aquifer's ability to recharge, there's an emptiness, there's a void in the aquifer. The ocean water pushing hard against the land has so much pressure that it forces itself into that void. And so salt water slowly seeps into the half full aquifer. And what happens when salt water mixes with fresh water? That's right, it's no longer drinkable. So we have a big concern as we continually pump water out of our aquifer that it recharge fast enough so that we do not have this problem called saltwater intrusion. Go through that process in your mind and understand what saltwater intrusion happens. It's not an issue in the Ogallala aquifer because it's in the middle of the United States. Saltwater intrusion is an issue only in the aquifers that are right along the coastlines. Again, a half full aquifer is going to have pressure on it from all of the ocean waters pushing, and salt water will slowly seep into the aquifer, and that makes the water undrinkable. Time to talk about surface waters. Wetlands, lakes, ponds, rivers, streams, all of these things are called surface water. And again, surprising to note that less than 0.5% of all of the fresh water on Earth is surface water. You can see here the volumes, the depths, and the surface area of some of the largest lakes in the world. This would be a nice trivia question, wouldn't it? What's the largest lake in the world? Caspian Sea, by far, when it comes to surface area and when it comes to volume. Caspian Sea. Here's our Lake Superior. The number 3 lake is Lake Victoria on the eastern side of Africa, and then a couple more of our Great Lakes. Lake Huron, Lake Michigan, Lake Tanganyika is in Africa, and then Lake Baikal is in Asia. And that's what we have here. We have a river floodplain, which is the mouth of the river. And the reason that floodplains and estuaries and other areas along the coast are so important is because of possible flooding. Rivers will not have the same amount of water all year round. Obviously in the springtime when the snows are melting, that feeds the river very strongly, and so that makes the river flow much faster. And of course that new volume of water being added to the existing river might force the river to jump its banks and flood. We'll talk about more about that in the next video when we talk about man-made devices we use to try to control river flooding. Lakes can be characterized with 3 different terms. You need to memorize them. An oligotrophic lake is something we also call a new lake. Picture one of those pristine, really cold lakes up in a mountain somewhere. Perhaps you visited one on vacation. Rivers that are up in the mountains are very cold because they are fed by those melting snows And that lake is just like a bowl, holding that cold, fresh water. Oligotrophic lakes do not have a lot of life around them. There's not a lot of algae inside, not a lot of plant life on the bottom. That's why it's sometimes called a new lake. Because that bowl is made primarily of rock. There's no soil down there for plants to grow. So there's not a lot of photosynthesis happening around that lake. So therefore there's not a lot of living things. Remember, net primary productivity? Very, very low in an oligotrophic lake. The eutrophic lake is the opposite extreme. And we've talked about what eutrophication is. I hope you can write down the steps to eutrophication. It's been what, like 5 or 6 weeks since you learned it? Why don't you test yourself right now? And in your notebook, jot down the steps of eutrophication. Well, the reason that we use that word is because eutrophic lakes have a lot of productivity. In fact, these are old lakes. They have sandy bottoms. There are lots of plant life down at the bottom of these lakes. Lots of photosynthesis, lots of algae on top, and therefore a lot of NPP. Lots of NPP means lots of fish, and of course we run the risk of an overgrowth of algae on the surface, and that's when we get that eutrophication. So think of a eutrophic lake as warmer waters, cloudy, algae, plants, lots of life there. And then meso in front of anything means middle. A mesotrophic lake is a lake that's not as new as an oligotrophic lake, but it has not met eutrophication yet. Meso means middle. Keep those terms in mind. Okay, the last thing to cover in this part of my video is atmospheric water. And you saw the pie chart, so you know less than 0.5% of water, in fact I think it was 0.03% of water is in our atmosphere. And yet that's very, very important for us because of rainfall. It was atmospheric water, or the lack of atmospheric water, that's caused some of the extreme droughts that we've had all around the world. Aridity means lack of water, and of course we all know about droughts that happen all around the world. Particularly arid countries rely heavily on that little bit of rain that they get all the time. They don't have lakes and rivers to rely on to pump water out of for agriculture, so they rely heavily on the rains. When we go through a sustained drought, perhaps 2 or 3 or 4 years of not having quite enough rainfall, these countries really have famine. They have severe starvation in their countries. And then things just get worse, because with lack of rain and lack of plant growth, then we have a problem with the soil getting airborne. Recall our Dust Bowl of the 1920s and 30s. We had year in and year out of drought, and then the winds come and move that soil really thousands of miles. I mean, it was reported that there was topsoil from Kansas made its way all the way to Washington, D.C. once that soil gets airborne. On the other extreme, we can have severe flooding in areas where for way too much of the time there's way too much rain, and that feeds rivers. It keeps the land from its ability to absorb so much water. It kind of oversaturates that soil, and you end up with severe flooding in other locations. One last thing to remember about rains and atmospheric water, and that is our introduction of impermeable surfaces. When you think of how much different the landscape looks today from 200 years ago, we're still having the same amount of rain, and that water's got to go somewhere. You'll understand how our addition of impermeable surfaces, roads, parking lots, all the blacktop issues, all of the large cities, with all of their buildings. All of this land area that we have used up that used to absorb rainwaters and it used to recharge aquifers. All of that now unavailable to us because of impermeable surfaces. Impermeable means it cannot be penetrated by water. So our addition, anthropogenic, remember that word? Our anthropogenic addition of impermeable surfaces has an effect on how water cycles from the atmosphere. All right, I think that's where I want to stop for today. We're going to learn about levees, dikes, dams, other human activities that we've done to alter where the water goes in the next video.